Let's start. This is an individualized review session. This will be both in D2L and in the written form, and also I'll put a link to the video recording. So this is review for exam 2. This is the 6 p.m. Monday session. How about if we handle this about the way we have before, some of these review sessions? I'll just walk through the pages in advance. You tell me which ones you think are highest priority. We'll tag them and do them first. If there's any time and inclination, we can go back and do some others here. All right, starting with the first page. I assume you all have a sample exam, practice exam. On that first page, what jumps out at you? Okay, so this set, okay, they're all tied to those structures there, so yeah, we might as well get them all. Okay, anything else? Next page, which looks like questions 6 to 11. What do you see there?
Can we do number 6?
Okay.
Number 9.
9.
And 11.
Okay. You know, while we're at it, okay,
Sorry.
and we might as well do 7, because that whole page is just packed with ideas. None of them, just terribly hard, but might as well get them all. Okay, next page.
Oh, 14. Because I know S and R. I'm kind of confused on L and D.
Okay. All right, so if that's the question, then we better do all those. This is turning into do all of them, I guess,
Oh, sorry.
but if that's what it is, that's what we'll do, okay? And that takes us down to 16. Anybody want to see that one?
Yeah.
Okay, I think looking at that one would be smart. Then that takes us on to the next page, 17, 18, and 19.
Can you do 17?
Sure.
Maybe 19. I don't know. 18.
Okay, any others? That page. Next page is 20 to 25. And that's a little cluster of questions that are all kind of tied to the same spot.
Can we do 20?
Yeah. We can do others if we get time. Let's take a look when we're on that page, just to make sure that we get kind of even coverage here. Next page, 26 to 29. What looks most important there?
Can we do 28?
28. Yeah, of the two naming ones, that's
We haven't did it in a while.
that's important. 29 is straight off an old exam kind of. I think we better do 27 while we're at it. Okay, those are the two naming things. If there's time, I'm going to put a question mark by that one. And 30, anybody want to see that? 30?
Yes.
Okay, of the ones that we went through, I think the only additions I would suggest might be more of these,
Yes.
because they're all kind of tied to the same thing. All right, that should be doable. Let's just go through those. If something else comes up along the way that you happen to notice, it's kind of like, oh, since we said that, I'm wondering about this other one. Let me know. We'll just kind of take it in as we go. All right, so questions 2 to 5 are all about this set of structures right here. And so the first one is about structure W. And do you have this practice exam on you? Okay. So question 2, in W, the ethyl group's position is, and there are only 2 options here, equatorial or axial. The one that's drawn here is straight down. The other one that is a possibility would be that one. There's just hydrogen there. So what is the ethyl? Is it axial or equatorial? Yeah, it's axial. It's straight down. All right, I'll just put on little notes there. Let me know if you need more. And then the next one, which is the most stable conformation of? Okay, now here's a little list in the name. Trans. And then you need a bromine and an ethyl, and you need them on cyclohexane. All right, so how about if we look around for things that aren't even 1-bromo 2-ethyl? All right, this one right here doesn't have both an ethyl and a bromine, right? It has a methyl and it has a CH2Br, but that's not even in the running. Okay, so it's not Z. And then notice 1-bromo 2-ethyl, and take a look at this one right here. You could call this one 1-bromo, but by the time you get here, you're to 3-ethyl. Now that's not even things on the right carbons, let alone getting to the level where you worry about where they're pointing. Okay, so this is not 1,2, and the first one had its own set of problems. Okay, now it looks like the other 2 options really are 1-bromo 2-ethyl. They've got a bromine on carbon number 1. You can start on either carbon you want. And next door they have an ethyl group. All right, so let's talk about whether they're cis or trans. This one, the bromine, points down, and that's true here as well. Now, don't get mixed up. One of them points straight down. That's the easy one to see, right? But this one right here, it still points down. Now, it's not straight down. But it's sure not in the other position. Axial on that carbon right there would be pointing straight up. It's not there. So that means they're pointing in the same direction. And this one must be cis. And let's take a look at this other one here. This one might fool you because it sure looks like they're nice and comfortable in the same spot next to each other, and they are. They're both equatorial, but that's not making a statement about whether they're cis or trans. This one points down, and this one points up. Not straight up or straight down, but a little bit up and a little bit down. Which means that this one right here has to be trans. And what were these choices again? The most stable conformation of trans. That would have to be B.
So when it says that means like they're both pointing the same direction?
Yeah, either both up or both down.
Okay, so it doesn't mean like if they're on the same side of that?
Well, they both kind of are on the same side here, right? Because this one points straight down and this one points down. If you were to draw that as a flat view of the ring, you know what the ring looks like when we draw it like this, you could draw it like this. That one's down, C2CH3, that's the ethyl group, and that one's down, bromine. Okay, now it would be just as correct to draw them both pointed up, because that would be cis. Either one of those are a way to draw cis. Okay, then the next one, what are W and X? Well, we've just said something important about them. One is cis, and the other one is trans. That fell out of our little comparison we did for question 3. And if that's the only difference between the two of them, you can start knocking out differences right away. You can say, well, they're not constitutional isomers. Constitutional isomers are way different from just saying cis or trans. That's just stuff pointing in different directions. Are they different conformations of the same compound? No. Cis and trans, remember what we said about them, can't be converted just by rotation around a bond or two. If they're different conformations, you can spin them, you can flip them internally, something like that. That's all it takes. Changing cis to trans is a much different proposition. Identical? No, not even close. These are stereoisomers. And that kind of makes sense because of what we've said about them. They're the same except for one thing, and that is where things point in 3 dimensions. That's a stereoisomer. Some of them mirror images of each other, some of them aren't. Okay, that's fine either way. Let's see. Oh, there are questions on that. Number 4. Number 5 asks us to compare, what is it? Y and Z. Okay, now these things are way different from each other. Y and Z. Notice, I guess what I'll say here is notice a whole atom, which in this case, bromine, relocated, and this would be between Y and Z. Another way of saying that is they have different connectivity. So they're much more different than just where things have to be sticking out in 3-dimensional space. And whenever you have 2 things that are that different, same formula but way different structure, what do you call it? Constitutional isomer, yep. Okay, those are all built off just those 4 structures there. Are there any questions about them? Yeah.
Just to clarify, stereoisomers, that's when they're located in different areas, but
No, that's constitutional isomers. If things have moved around inside the molecule, that's constitution. Their constitution has changed. Stereoisomer means they look the same except for where things point. All right, here's another page worth of some 3D stuff. All right, which one of these, in question 6, is chiral because it does not have an internal plane of symmetry? Well, the way to solve this as quickly as possible is to just look for ways in all of these that you could split the molecule in half and have identical halves on either side of a mirror plane. And it's pretty easy to see with that 4th one. It's got 2 halves that are the same as each other. This one right here is not too bad to remember as long as you keep in mind that it's actually a tetrahedron in 4 dimensions, 3 dimensions. So there would be not just one, there'd be 3 mirror planes that could split that one in half, and you'd end up with identical halves. And then the same would go for this one right here. Straight down the middle, there's a mirror there. And that just leaves you then with C. That one's an amino acid. Okay, then the next one, part 7, just gives you a couple of names as words and asks you to say what the relationship between the 2 of them is. Here's what you're looking for. Key in on this. Now the words themselves are identical. It's 2-bromooctane. And the only difference between the 2 names of the 2 compounds is R and S. If that's the only difference between the 2 of them, they are automatically what? R and S we use to describe one enantiomer and the other enantiomer. That's what this means. That's a quick answer that you ought to jump to because you understand it. R and S. Okay, the only difference between the two of them is R versus S. Okay, then the next one, part 8. The standard rotation of D, and then it gives you this compound, is what? Anybody want to take a stab at that one? All you're given is that the conformation is D. That's the relative conformation. Remember we talked about two ways of calling a conformation, R or S, D or L. And here's one of them. That's given. That'd be a real compound. Okay, standard rotation. You don't know. You have to be given, you'd have to be given the standard rotation of the L isomer. Then you'd know. Same number, opposite sign. But there's no way that you can look at a compound and see D and then jump from there to saying, aha, I know which direction the light is going to rotate, either positive or negative. Nature has not handed us that kind of world. We're on second page. Okay, that's question 8, and question 9 is similar to it. Okay, but the story changes a little bit right here. You're given this. So we're talking about an enantiomer that has the R, absolute configuration, and we're also given this. We're given its absolute rotation. If you put the R enantiomer into a sample cell, it will turn light in a negative direction. So the standard direction of S, and notice that, is just the other enantiomer. It is positive. Yeah, that's all you know, but that's actually quite a bit to know. It has to be this, it has to be the same number, it has to be the opposite sign. You'd say it's A. Okay, does everybody get kind of how these two questions, 8 and 9, are an evil pair of, like an evil pair, evil twins? Okay, so let's skip 11. Seemed like there wasn't demand for it. We can come back later if you want to. And now let's take a look at this one right here. This is now giving you a structure, a couple of pairs of compounds. And the question is, what are they of this list right here? Well, one thing, they're not constitutional isomers, right? You've got an ethyl group and a methyl group, next door carbons to each other. The only difference is that this one points straight up, this one points straight down in Y. So what do you call this first one? Do you call it cis or trans?
Trans.
Yeah, this one's trans. And this other one is cis. This one of the two, it would be the harder to see. This one is pointing down, so is this one. All right, so let's start talking about what might work and what might not. Are they constitutional isomers? No, not even close. Things would have to move around within the molecule to different spots. That's not it. Different conformations? No. And the reason you say that is you can't convert cis to trans just by rotation. It takes something more drastic than that. You got to break bonds and reform them. Okay, of these two right here, you're then left with deciding Well, first of all, let me put the big conclusion on these two terms. If one of them is cis and the other one's trans, and that's the only term you have to put on it, what you can say is that they're not conformations of each other. So we know that. They're not constitutional isomers. They are stereoisomers of each other. Now, that's always true when you compare a cis and trans pair. Okay, so they're stereoisomers of each other, and there's just one more step, which is part C and D, which says, okay, so which kind of stereoisomers are they? Are they mirror images or are they not mirror images? Remember, diastereomers are not mirror images of each other, and enantiomers are mirror images of each other. So you just eyeball those and you go, are they mirror images, yes or no? What do you think? They're not. So that makes them C. Okay, you can tell by just drawing them, or run a mirror plane between them or something. You can tell that they are not mirror images. Okay, any questions on that page? Yeah.
So what would make them mirror images then? It looks like it's supposed to be a picture.
Yeah, you would have to draw this one backwards. So run a mirror plane right here, and then redraw the ring so that the ethyl group is facing the other way, and it's up, and the methyl group would be down. If you want to do that, why don't we come back to that?
Okay.
That's a little more advanced question. I'm glad you're probing it. So her question is, what would it take to turn this into its enantiomer? What would we have to draw differently? Yeah. Okay, so let's make some progress here on this next page. 12 to 14. And they're all about that set of four structures. Okay, starting off, and we got a couple questions probing the term, the relationship between some of these structures. Excuse me. So we're starting off by comparing Y and Z. Those two. And what you want to look at is, are they different conformations of the same compound? No. You can't convert one to the other just by rotating around bonds. The next two you might want to think about pretty seriously, but let's look at constitutional isomers. No. Okay, and the reason you say that is no atoms have been relocated to different parts of the molecule. So that one's out. Everything between those two is bound in the same order. You got two carbons in the middle. Each one of them has an H and an OH. One of them's got a methyl, one of them's got a CH2OH, same story here. Really the only difference between the two of them is where the hydrogen and the OH sit. And so you can run yourself a little plane right there and ask the question, are these two mirror images or not mirror images? So what's your call? Yes or no? Are they mirror images or yes or no?
Yes.
Yeah, they are. Okay, so that means that you can tell that by just inspection. So the fact that they are mirror images, so they are what? Enantiomers or diastereomers? Yep. And that would be what? That would be choice C. Okay, and then we're asked to compare W and Y. That'd be what? These two? across the way there, and I think you can tell by eyeballing that again, they're not different conformations of the same compound, and they're also not constitutional isomers. So then you're down to trying to maybe ignore X here in the middle. Imagine yourself a mirror plane split in between the two, and what would you say? The mirror images, yes or no?
For W and Y?
From W and Y.
No.
Yeah. They're not. Yep. So these two, they're not mirror images, but let's even add something ahead of that. And let's say, well, it doesn't matter that they're not mirror images. They definitely are stereoisomers. What kind of stereoisomers? Well, they're not enantiomers, so that just leaves diastereomers. That would be the answer you want for part B. Okay, and then number 14. There's a minefield in the answer right here. It asks you for the relative configuration of Y, and it could have been any of these in this box up here. Same question would have worked. Relative configuration cannot be expressed as R or S, right? That's absolute configuration. That's what we started with. So whatever your answer is, it has to be either D or what's the other one? Remember? D or L. So D means dextro for right, L means levo for left. And what you're looking for to make this call is look at Y, which is that one right there, and you're going to go for the OH group that's on the last chiral carbons, next to the last one in the whole chain. Okay, and that one is on the right. Off the screen. And that means you call it D. You're done. You look at that one OH, look at where it sits, forget trying to come up with priorities like 1, 2, 3, and 4 and stuff like that. That's where we were today. So this one is D, and let's see, that's choice C. Okay, questions on that one? Okay.
For 14, why do we look at that specific OH and not the other one?
That's the definition of D versus L. There can be dozens of carbons in a row. The only thing you look at is this last chiral one in the chain. As long as you look at that one and you look at the right thing, which is where the OH is, that's all the information you need. It is simpler. It's also not quite as generally useful, but it does work for some things. Okay, this last one here, number 16, was requested maximum number of stereoisomers. Now, there's a minefield in this one too, and that is you may be tempted to look at it and go, well, you know, anything with an OH on it is a chiral carbon. Oh, sorry, go ahead.
Did you answer the wrong one? You wrote C, or like
Oh, wait a minute. I did. That answer goes there. And let's, oh, somebody did ask for that one too. Okay, let me go back and pick that one up then. Looks like that one's circled. Okay, so that one should, 14 is the one that should be C. And this last one right here.
Isn't 14D since it was right?
Was I reading this one? Yeah, it's reversed down here, right? I picked my choices from down
Yeah.
here because I was reading down here. It should be D.
Which is like,
This one, let me add to the answer. Okay, this one is on the right side. So it's D. And that is a multiple choice. Yes, is D. Okay, thanks. I'm on the right question now. Okay, this next one, which is also asked for, also has a minefield in it, absolute configuration. If you're asked for absolute configuration, your answer can be only one of two letters, and those two letters are what?
R.
R or S, yeah, okay. So that puts us off into a different zone. R or S, not D or L? All right, those are two, again, evil twins with mistake possibilities in opposite directions. And this one is what we started with. You'd start with the biggest and littlest atoms out from the central carbon. OH is the biggest, hydrogen's the littlest, and then the tie in the middle you break by moving past the carbon. This one would pretty clearly get you into bigger territory quicker, so there's 1, 2, and 3. And good news is that hydrogen is already back here. Whoever wrote this question was apparently kind of lazy, and just wanting to make it quick to grade. So it's that direction, and what would you call that? R or S? Yeah, it'd be R. So let's see, of the list, that's, here, label that. So this would have to be A. Choice A is R. Please not C or D. It's not D or L. Stay clear out of that territory. Okay, the last one, now that I've gotten over skipping things in the middle, is there's a trap here, and that is just going, oh, well, wherever there's an OH, it must be chiral, but not really, because that one right there, that one's not chiral. It has 2 hydrogens on it. 2 hydrogens, 2 of anything the same, knocks a carbon out of the running.
How can you tell if it's chiral or not?
You're looking for, let me write that definition down here. A chiral carbon means that it has 4 different partners. They all have to be different from each other. Well, and that means that this one's also out of the running. This one's not chiral. It doesn't even have 4 partners, let alone 4 different partners. It's not even up to the right total. And the other one to knock out would be this one right here. That one's not chiral because it has on it 2 hydrogens. They're the same as each other, so we're not even in the right zone. All right, that just leaves then as possibilities this one, and this one, and this one. I guess that's the only 3. You look at those carefully, you'll see each one of those carbons has got an OH that is drawn and hydrogen that isn't drawn, and then very different stuff in the 2 different directions of the molecule. Look what this one sees. It sees double bond O and that, and then going this direction it's a neighbor with an OH, another with an OH, and all this stuff out here. Everyone sees something different. So you're down to 3 carbons that are chiral here, so that means that N equals 3. It's green, yeah. And 2 to the N is 2 to the 3rd, which equals 8. So there's the answer to that one. Any questions?
Where you wrote not chiral, could you explain why that one isn't chiral?
This one here?
I would have one that
Okay. This one is not chiral, and the reason is it doesn't even have, is that all fitting? Yeah. It doesn't even have 4 partners. And that kind of goes back to the earlier question, which is what does it take for a carbon to be chiral? It has to have 4 partners, and they all have to be different from each other. Well, this poor thing right here, it's got 1 partner here, and 1 partner here, and 1 partner here. Just 3. Not even in the running.
I missed the double bond.
Oh, the double bond? Yeah, that would be important. Yeah. Yeah, it's got 2 bonds to one of its partner, but it's still just a partner. Okay, questions beyond that? All right, looks like 2 were requested on this page. And the first one is just about this compound here that's drawn on the left. That's the bond line drawing, and then you're asked to go to Fisher projections. It usually is useful, you don't have to do it this way, but at least remind yourself of how many carbons you're going to need to draw when you're all done in the other version of drawing this thing. And so I guess I'd say, well, we're going to have 1 there, and 2 and 3 and 4 like that. And then you just put in what you see in the first version. So there would be a CH3, that's carbon number 1, that's all it has on it. Bromine. Now you're only asked to draw 2 possible stereoisomers. There's several correct answers right here. I'm just going to do it the lazy, quick way so that it's easy to tell the difference between the 2 of them and make sure that you really have gotten 2. So I guess I'd start off with the bromines on the same side, and then maybe one with the bromines on different sides. Not intended to be mirror images of each other. That's okay. And then just cap off the way you know you need to, both carbon 1 and carbon 4 as it's drawn here to begin with. Those are just methyl groups, one on either end. And the carbons that are chiral, each of them has a bromine and a hydrogen, which isn't drawn in the starting view. Okay, there would be other correct answers. Now, of course, there are wrong answers too, but there's more than one right way to do that. These right here, not intended to be mirror images. So, and here's a review term. They are what? They are stereoisomers of each other, just because they're different by where things point. They're not enantiomers, so what are they?
They're stereomers.
Yep. All right, I'm not sure what more to pull out of that one. Are there any questions about it? Yeah.
Can you replace like the bromine and the hydrogen? So let's say you have like the bromine on top and the hydrogen on the bottom on the same side. Would that
Oh, I
work
see what
too?
you mean. Could you have the bromine up here?
No, like so you see where the bromine's at right here. Like you keep that right there, and you have a hydrogen instead of the bromine on the same side.
Oh, hydrogen here instead of bromine.
Yeah, or like vice versa.
Okay, I'm glad she asked that, because if you draw a hydrogen and not a bromine, maybe you're asking, could I move this bromine down to here?
Yeah.
Okay, that's a valuable question. If you do that, what you've done is you've created a constitutional isomer. Right? It's not even the molecule that's drawn here. The molecule that's drawn says the 2 middle carbons, each one of those guys has to have its own bromine. But if you drew something over here that says 2 bromines are sitting on the same carbon, that's not even this. It's a different molecule. So let me draw it just kind of in parentheses. Here's what you're asking about. I'll draw this little. You would say maybe something like this.
Kind
Kind
of.
of?
What I was like more like referring to was having a hydrogen and bromine on one side and a hydrogen and bromine on the other side. Would those be?
You mean like this one?
anchors?
Like this one?
Yeah, but can you like flip it to the other side as well?
Oh, I would, and draw a different structure, kind of like the mirror image of this one.
Yeah.
Yes.
Oh.
Yes, that would still be correct. This is just 2 that happen to pop out. In fact, the important thing is to probe exactly what I thought you were asking. You weren't asking this. What you don't want to do is move the bromines around so that they're like on totally different carbons. Each one of those middle 2 got to have 1. And you can't put the bromines on the ends. You can't put them both on the same carbon. At least get from here to here with everything riding in the spot where it should be. All right, 19. I think I'll do this by two different options and show you some pitfalls here. And it just starts out with this bond line drawing, and you're asked to draw and label both enantiomers and make sure that the mirror relates the two of them so that you can tell which one is supposed to be which. I'm going to kind of extend this up here, and let's say here we have option 1. A decent way to do it is to start with this thing and just kind of change as little as possible. Keep it pretty simple and recognizable, and draw it almost the way it is. So left to right, that much will work for you. We have what, 1, 2, 3 carbons, so there they are, 1, 2, 3. But here it's heads up, because if you just fail to draw any stereo view at all, no wedges, no dashes, nothing like that, if you just take this right here, you haven't drawn one enantiomer or the other. Okay, and if you want to do it this way, once you've got this drawn, it's not too hard to get yourself to the other enantiomer, because you just say, well, okay, I've got my bromine here, and then I've got 3 carbons, 1, 2, 3, and then far away from the mirror, OH, and the reflection still coming out at you has bromine. Okay, notice both of these are stereo views. That means that they've got at least a wedge or a dash, something somewhere, so that you can tell where things point in 3D. Okay, that's one way to do it. Here's option 2. And option 2 is start with something that we started with and that you're all pretty comfortable with. Start with a tetrahedron. And we'll say that this is going to represent that 1 chiral carbon in the molecule. And I just start with the tetrahedron itself, both of them, and then come back and stick stuff in place. So that's what you'd be looking at for your 2 tetrahedrons. All right, the wedges come out at you. The dashes are both pointing at the mirror. Solid lines straight up and straight away from the mirror. And then just carefully put in everything as the order looks kind of like it is here. If it would help you, just envision a hydrogen back there. I'm going to put that in parentheses. If you don't want to put it there, don't worry about it. So I guess I'd start by saying, okay, hydrogen's back. And if I start with the hydrogen back on the left structure, it has to be there on the right one as well. And then just look at what would be kind of easy. Left in this initial drawing has OH, so it would be in the mirror image over there. Looks like bromine's kind of pointed straight up, no problem. Put it in place, and the only remaining spot then is the rest of the molecule. And here's where things can get kind of hairy. What you need to do is make sure that you're just carefully tracking what's there. It looks like we have bound right to that chiral carbon. We've got this thing right here, which is a CH2. And next in line is a CH2, but it has a bromine on it as well. And then this one right here, CH2, CH2, Br. Okay, there's option 2. Stop and see if you're following both of those. Oh, I'm just curious, which one do you think is easier? The top one? Okay, that's fine. What you don't want to do, somebody always does this, they want to just take this bond line drawing and draw it, and actually draw it, okay, and then come over here and draw its mirror image. And do that okay too. But the problem is, if you don't start with a stereo view, you haven't drawn a mirror image. So as long as you get off to a good start, yeah, this probably is quicker. I think I'll skip the R or S for now, just to keep us on track with time. And we can come back to that if you want to. Oh, hey, okay, here's a little hornet's nest on the next page, 20 to 25. And all these questions says refer to these Newman projections. There are 6 of them. And don't freak out about them or anything like that. The most stable conformation. Now remember, the most stable is everything as far apart as possible. All right, just looking at that, you might tell your story kind of like this to begin with. I see 2 carbons. That's what's always at the middle of these things. One of them has a 3-carbon group on it, propyl. The other one has a 2-carbon group on it, ethyl, so those 2 kind of go together. 1 on one carbon and 1 on the other. And it looks like this whole story is just them swinging past each other on next door carbons. And so of that list of 6, which one do you see that looks like it puts the propyl group and the ethyl group as far apart as you can get them? Yeah. Okay. And there's your reason right there. The big groups are as far apart as you can get them. All right, this next one, there's a gauche interaction. Okay, this is a special term that means 2 things, I guess, keep in mind. Not eclipsed, but not anti. So they're not as far apart as they can get. Not like that first one. All right, let's take a look at our characters again. Do you remember what eclipsed means? It's like drawn right on top of each other, right? And which one of those structures do you see that look like they're drawn right on top of each other? There should be 3 of them. Good. Okay, this one's eclipsed. So's this one. And so's this one. There's clearly crowding going on there. Well, this one right here is not going to be B or D or F. So there's a gauche interaction. It's not anti, meaning your 2 biggest groups are kind of close to each other. They're not as far apart as they can get, but they're not on top of each other. Well, we're only looking at C and E, and so we're told that the answer includes C. That's a gauche interaction right there. I'm told that gauche is a French word that means just kind of awkward. Does anybody speak French or taken it? It just looks like there's something not quite right. It's not as stable as it should be. And that means that the answer then would need to be C and E. Okay, and right here in this spot is the reason you call that one gauche. Okay, circle all terms that correctly describe structure A. Okay, we're back to now the one that's the most stable. And what would you say? Is it eclipsed? No way. It's nice and relaxed. Is it staggered? It is. Now there's more than one way to be staggered. Okay, both of these are ways to be staggered. And of those 2, anti or gauche, which one is A? It's A, yeah. It's anti. All right, and then a similar question for part D. Structure D is this one right here. It looks like everything in the world is wrong with it. Right? It has things bumping into each other. That thing is a mess. Okay, so what would you say? Is it eclipsed? Yeah. And it's not staggered, and for that reason, it's not either one of these as well, because both of these are different versions of staggered. All right, as this molecule rotates around this one bond, question 24 is asking us, it spends the least amount of time in which one do you suppose? D. The reason for that is it's the most crowded. Now that's just kind of a word version of the question, a story version of the question, which you can plot on axes like this. And the plot itself tells you a little story. So it says, label the curve with A and C in order to show where these conformations are represented. Okay, now remember, A, we've come through this story up here. A is the most stable. And C is not too bad. C, remember, is staggered, but it's not the best. It's not anti. So it ought to be possible to kind of put a letter on that diagram to show where they come. The lowest point that I see is right here, and it would also be okay to put an A there because it's gone through a full rotation and come back to it. That's as stable as it possibly gets. Lowest energy means the most stable. So it'll spend as much of its time looking like that as it can. And then you're left with just a few points. If you had to guess, would you put C at the top of a hill or at the bottom of a hill? I should say the top of a hill or a valley. C's in a valley, right? It's more stable than some of the other awkward things. So C would be there, and what was the other one? E. C can, and then in the middle, your hilltops. What are those? B and D and F. Those are the ones that are awkward. They're hard to do. They get out of that configuration as soon as possible if they get in it. Yeah, eclipsed means these are the most prone to change, and your wording was reactive. All we're talking about is moving from one conformation to another, but in the rest of the course we're about to get to the point where up here means you're going to go to a completely different molecule. And that's what reactivity means. Yeah, the top of an energy hill. Thought I saw another question. Anybody else? Okay, moving on. I have a question mark by 27. I think nobody asked for that one, so let's do number 28 as priority on this one. Start with the last part of the name. If you're given a name and asked to go to a structure with it. So undecane means carbon, that's 11 carbons in a row. And cyclohexane, cyclopentane, you know what those mean. Either 6 or 5 carbons in a ring. Okay, so let's do this number 11 thing. So 2, 4, 6, 8, 10, 11. There's 11, and we'll just put on a few numbers here. Looks like we'll need to locate 3, 4, and 5. And let's just put on what we find in order here. It looks like the name says 5-isopropyl. So on carbon number 5, you do that. That thing right there is isopropyl. And then what does the name tell us next? It says there are 3 methyl groups. 2 of them live on carbon 3, and 1 of them lives on carbon 4. Okay? There are your 2 methyl groups on carbon 3. They both need to be bound, connected to their partner, which is carbon 3. And number 4 also has 1 on it. And that's getting to be kind of a crowded piece of organic chemistry there, but that's where you get. Now the next one, cyclohexane, says that the ring can be drawn flat. Oh, how nice is that? Okay, just draw your ring flat as a hexagon, and you can literally start on any one of those carbons you want to and call it number 1. I guess I'll do the easy thing and start up here 1, and if you're going to count around, you get to carbon 4 straight across from it like that. And it's dimethyl, and they need to be cis compared to each other. Don't forget the cis part. Okay, either point them both straight up or both straight down. And don't forget the cis part. And then the third one is cyclopentane. That's the parent compound. So like that. And tert-butyl means take your pick, any carbon you want. Draw a tert-butyl group coming off of the ring. It needs to be hanging on to, the tert-butyl group needs to be hanging on to one of the ring carbons. Butyl, tert-butyl, hope you recognize it's 4 carbons. That's what any butyl means. Tert means there's a tertiary carbon in the middle. It has 3 carbon partners, which are these 3. Okay, questions about any of those 3 names? And I think I got a question for this last one as well. You're given a number formula just to use. You don't have to memorize that, just know how to use it. And I guess know also what not to use. These right here are not relevant to the final answer. Those are the answers you don't use. The ones that you do use right here are these 2 numbers right here. So starting with the millimoles of major product, 50, you get that one as the major product just by looking at this other one and saying, oh, I'm getting really educated. I can recognize that 50 is more than 48. There's those 2. And then the other thing that you need to remember to do is not take the difference on the bottom, but add them. The total millimoles is 50 plus. And don't forget your times 100%. If you run that through a calculator, as I did recently, you will find that that's 2.0%. Which is not very good. That's saying it's a mixture, about a 50-50 mix of the 2. Well, that may be what you need, depending on the product use. Okay, what other questions do you have? We kind of went through what everybody prioritized, and there may be a few that you noticed as we went through that were kind of like, ooh, I wish I could see that one while we're at it. 26? Okay. So this one starts you with a Newman projection. This is looking down just one bond. And the question is, though, so what compound is this? If you didn't mess with drawing it in this complicated fashion, what would it be? Well, you're going to be looking, as always, when you've got a name or a structure, for just the longest chain you can possibly find, and then put a few things off of it to get yourself to the right structure. Here's the one that's nearest to your eyeball, and everything on it is these 3 right here. You've got a hydrogen, you've got 1 carbon in that direction, you've got 2 in this direction. Okay, that's 3. That's carbon number 3 right there. And the reason you know that is you can get to that as the longest chain by starting here and calling those 2 carbons 1 and 2. One farthest out at the end, you're starting there, going to 2, then going to 3. Then back behind is number 4. You'll never see it. But carbon number 4 has several things on it. Okay, it has a hydrogen. It's got one carbon. If you go one direction, it's got three carbons. If you go the other direction. Okay, 4 you don't see, but you know that you can keep going as long as possible if you call those 5, 6, and 7. All right, so you've learned something about the molecule. The longest version you can get out of it has got 7 carbons. 3, 4, 5, 6, 7. And the one we happen to be looking down is 3 and 4. So then let's think about what carbon number 3 has on it. It's got 1 and 2, so there they are. But it also has this methyl group. And I think what I want to do is say this one right here, that's the methyl group on C3. I'm sorry, this one is the methyl group on C3. So drawn on C3. Now it turns out that C4 also has a methyl group on it. So this one is on C4. All right, then let me simplify that. 7 carbons, 2, 3, 4, 5, 6, 7. And all you're looking at is that and that. There's 3, there's 4, there's 7. Not that complicated once you draw it out, as not many numbers, just the minimum number of carbons you can get away with. Okay, what else? 29. Okay, here we go. Now this is a good one to be going after because it's just a repeat of things that come up on quizzes and exams in the past. This is kind of keep you going. So it's predict a reaction between a Bronsted acid and base, and so the main piece of news that I would ask you to notice there, the fact that it's a Bronsted acid and base means that a proton is going to change hands. Okay, you're asked to predict the products and draw curved arrows correctly. All right, this one right here, the first reactant has only one hydrogen in the whole molecule, and it looks like it's on an atom, oxygen, that's more electronegative than nitrogen. So this one you can kind of tag as the character it is. First one's the acid, and the second one's the base, which means that you can expect the acid to lose its proton and the base to gain the proton. All right, so here's what you do. Start on a lone pair of no, I'm not being dramatic enough. You start, okay, on a lone pair of electrons right there on the base, and you draw straight to the proton, and you make your arrowhead there. There is going to be a new bond between the base and the proton that leaves, and because that happens, the proton says, okay, electrons that used to hold me onto oxygen, out you go. You're onto just oxygen by itself. Okay, now good news is, if you drew your curved arrows correctly, there's almost nothing to do over here. You just have to show the fact that where there used to be that proton, you now have the pair of electrons. It was the bond that held the hydrogen in place before the hydrogen left. Negative charge right there. And now there's going to be a new bond between the base and the hydrogen. Plus, the base has all this stuff that it started out with. Formal positive charge, it's right there. Two curved arrows. The base reaches out and grabs a hydrogen, the hydrogen turns loose. And there are your two products. Here's the critical thing to notice. The hydrogen is now in a different molecule. That one hydrogen that we track. Okay. More questions? These have all been good. Yeah.
Would there be a flush charge on the hydrogen, or is there already?
You mean right here?
Yeah.
Yeah, there is. Right there.
I didn't see.
I think I didn't draw it big enough.
And then, my second question, can you just go over one really quick?
Which one?
Number one.
Oh, the number one. Yeah. Okay, what you want to notice about these is what's not different amongst them. All of these they should have the same number of carbons. 2, 4, 6, 8, 2, 4, 6, 7, 8. All of them are C8. So that much is not going to change. That means that they all have the same molecular weight. So whatever difference there is about boiling points between them, you can't blame molecular weight. They all weigh the same. But what you can do is look at the shape, and you say that on this end, it's the least branched with a given number of carbons. This end right here is the most branched. That means that the first one is the most like a little ball, doesn't interact as well with its partners, other molecules like itself, doesn't stick to them as well, and that means that A, with the lowest amount of force between like molecules, it's pretty easy to separate them from each other and boil them off. By the way, that first molecule is isooctane. It's used to set 100 octane in gasoline. So if you had a tank full of straight iso, it's called isooctane, 100% that, you get an awesome octane rating in your gas. I don't know what they charge you for that. Premium these days is what, 93? Forget what the rating is. I think premium is 93, and that's what you pay the most for. The worst compound you can have in your tank is not C7, but C8 as a linear chain. Oh man, that stuff has an octane rating of 0. You basically couldn't run it. Okay, that was a diversion. Okay, questions? Okay, are you feeling more confident or less confident?
More confident.
Okay, now the way to really test yourself is just print this out or use it online or something like that and do it all again. Okay, just see if you can reproduce what you got here with the reasoning and everything. If you can, yeah, that's a good start. Okay, I guess we'll call it good then.